Hello everybody, Namaskar. So I have already discussed three type of modification for the vapor compression cycle. So now I will discuss that if the temperature difference in between the evaporator and condenser, so how we can modify the that compression process, which can give rise to the performance of the system as well as the to avoid the various complexity by using the single stage compression or single stage system. Okay, so first of all we need to know that why we need the multi-stage refrigeration system. What is the difficulties in a single stage refrigeration system? So by using this figure we can discuss this matter very clearly. So let's say for example you have a that basic cycle 1, 2, 3, 4. Now if we increase the temperature difference in between the condenser and evaporator, which is called the temperature lift of the cycle. So if we increase the temperature of the cycle, so let's say if we decrease the evaporator temperature from 4 to 1 to 4 dash to 1 dash, or maybe 4 dash to 1 double dash. Okay, so if we decrease the evaporator temperature, then we will see that the temperature difference in between the condenser and evaporator, that will increase. And if the temperature lift of the cycle will increase, then what are the difficulties or what are the negative issues we will face by using a single stage vapor compression cycle. So we can see that one is the throttling loss that will increase by using the multi-stage using very high temperature difference in between the condenser and evaporator. So the initially that area the right side, so that area in between the 3 to 4, and that area now has been increased in between the 3 to 4 dash. So the right side area, that mark area, that area is basically represent the throttling loss. And you can see that if we decrease the evaporator temperature from 4 to 4 double dash, then you will see that the throttling loss of the system that will increase. Then if we see the superheat horn, okay, so superheat horn, which I have already told that this is the extra work needed for the compressor if we compare this cycle with the isothermal heat rejection process. So that you can see that this area will increase at will decrease the evaporator temperature. So if we decrease the evaporator temperature 0.1 to 1 double dash, then you will see that the outlet of the compressor that will be changed from the 0.2 to 0.2 double dash. So the area mark in this diagram, so this is also called the superheat horn, and this superheat horn or superheat loss that will increase by using the higher temperature difference in between the evaporator and condenser. And also another thing, you can see that as we decrease the evaporator temperature, that means as we increase the temperature difference in between the evaporator condenser, then you will see that your discharge temperature that will increase. That means the discharge temperature at 0.2 double dash, T2 double dash, that is higher as compared to the T2. So compressor discharge temperature will also increase, and the quality of vapor at the inlet of the evaporator that will also increases. Okay, so quality of the vapor at 0.4 double dash, that is higher as compared to the quality at 0.4. So quality of the vapor at the inlet of the evaporator that will also increases, so which will give the lower specific cooling capacity of the system. And for this case also we can see that as the inlet compressor condition, if we change from 0.1 to 0.1 double dash, then you will see that the specific volume that will increase. And if the specific volume will increase, so that will basically increase the volume flow rate in a compressor, and that will ultimately increase the total size of the compressor. Okay, so that means if we use the single stage system for a very high temperature difference in between the evaporator and condenser, then we will see that the different problem that we will face. Okay, different problem that we will face. So that is face. So something very important like that, the compressor discharge temperature, that is very important parameter. So that will become very high by using the single stage system, and another is the compressor work. Okay, so basically we have to target this especially these issues, the compressor work and compressor discharge temperature. So the initial modification, first type of modification, we will see that how we can use the how we can reduce the compressor work and compressor discharge temperature. So for this case we have to use the multi-stage compression system, and some other type of modifications that will be related to the multi evaporator system or related to the cascade system. Okay, so basically first of all we will concentrate that how the compressor discharge temperature, compressor work can be reduced by using the multi compression system, and which will ultimately give the overall performance or improvement of the system. Okay, so first of all we will discuss the multi compression system. The instead of on compressor or on compression process, we will use the two compression process. That means the compression from the evaporator temperature to condenser temperature, that will be done in a two stage. Okay, so the first, there may be the various configuration of the multi compression system, but I will discuss the three modification for the multi stage compression system. So first modification, so for this case we will use a intercooler in between the two compression process. So that means that we will use the two compressor instead of one compressor, and between these two compression we use the intercooler. Okay, so for this case you can see that the other processes are basically same as compared to the basic cycle or basic single stage system. So that condensation process 4 to 5, that is same. 5 to 6, this is the isenthalpic expansion process, that is also same. 6 to 1, this is the evaporation process or the heat addition process in the evaporator, that is also same. But for using for this case, we are increasing we are compressing the refrigerant vapor from the outlet of the evaporator in a two stage or by using the two compressors. So on compressor, that means the compressor on, this is also called the low temperature compressor, that can be compress the vapor at the outlet of the evaporator from point 1 to 2, and then at point 2 this is the superheated vapor, and superheated, so we can cool this superheated vapor by using intercooler. Okay, so in intercooler we can use some liquid to reduce the temperature of the refrigerant after the first compressor. So that with the temperature of the refrigerant vapor will reduce from the temperature T2 to temperature T3, and then this is going to the second compressor, which is used to compress the refrigerant vapor from the intercooler pressure to the condenser pressure. So basically this system is operating between the three pressure level. One is the evaporator pressure, and at the intermediate there is a intercooler pressure, and then the condenser pressure. Okay, so this cycle we can represent in a temperature entropy diagram and enthalpy diagram by this way. So what I have already told that there is a change in a compression process. So for this case the compression occurs in a two compressor. So the first compressor, for this case your process 1 to 2s, this is your isentropic process in a or isentropic compression process in a low temperature compressor or first compressor, and the 1 to 2, this is the non-isentropic process or non-isentropic compression process in a low temperature compressor or compressor on. Then the point 2 is basically the superheated condition, so that refrigerant at point 2 that can be cooled by using the intercooler. So for this case we are assuming that this cooling process 3 to 4, this process is up to the saturation point at that pressure. Okay, so in a intercooler pressure, the outlet of the intercooler, that condition we can assume as a saturated vapor condition at point 2. So 2 to 3, this is the intercooling process in a intercooler. Then the 3 point is again the saturated vapor at the intercooler pressure. Then this is again compressed in a second compressor. So the 3 to 4s we can assume as a isentropic process, and 3 to 4 we can assume as a actual process or non-isentropic compression process. Okay, so now the 1 to 2 is the compression process in a first compressor. 2 to 3 is the temperature reduction process in a intercooler, and then 3 to 4 is the compression process in a second compressor. Okay, so this thing we can represent in a pressure enthalpy diagram also. The 1 to 2 is the compression process in a first compressor, 2 to 3 is the intercooling process, and 3 to 4 is the compression process in the second compressor. And then 4 to 5 is a heat ejection process in a condenser, and 5 to 6 is a isenthalpy expansion process, and 6 to 1 is a heat addition process in a evaporator. Okay, so for the calculation procedure for this system, we can use the that property software or property subroutine in case of software application or numerical application. But for the by paper and pen, if you solve this type of or if you want to calculate or evaluate the performance of this type of system, so we need the property table. Okay, so from the property table we need to know what are the saturation properties, that means the enthalpy, entropy, specific volume, etc. at the different temperature. So for this type of cycle, if the 3 pressure or 3 temperature are known to you, one is the evaporator temperature or evaporator pressure, another is the condenser pressure, and third one is your intermediate pressure or the intercooler pressure. So if the pressures are known to you, so from the saturation table we can see that the 0.5 is the saturated liquid. So the we can get from the table, and that 6 H5 is equal to H6, and again we can see that the 0.1, 0.3 both are the saturated vapor points. So directly we can get the different properties from the table. Okay, so then basically when we are calculating the process 1 to 2 and 3 to 4, then we have to calculate the state point 2 and state point 4. So if we want to calculate the state point 2 and state point 4, so basically the 2 compression process are there for this case, and both the compression process we can use the similar procedure which we have discussed for the single stage vapor compression cycle. So basically that 1 to 2s, this is the isentropic process, so that the entropy at point 2s, that is equal to the entropy at point 1, and point 2s basically we know what is the pressure and what is the entropy. So we can calculate what is the enthalpy, and by using the isentropic efficiency of the compressor we can calculate what should be the enthalpy at point 2. Similarly for the process 3 to 4 also, the at point 4s the entropy is equal to the entropy at point 3 and pressure is equal to the condenser pressure. So we can get the enthalpy at this point, and then we can calculate what should be the enthalpy at point 4. Okay, after the second compressor. So by this way the enthalpies at the different point of the cycle that we can evaluate. Okay, so after the evaluation of the enthalpies of the cycle, then we can calculate the performance parameter of the cycle. So that is the cooling capacity that we can write in by the m dot into H1 minus H6. Then we can calculate the compressor work, low temperature compressor work, m dot into H2 minus H1. Then we can calculate the compressor work for the second compressor, that means the high temperature compressor, that is m dot into H4 minus H3. So ultimately we can get the COP of the system by using this equation. So the cooling capacity divided by the total compressor work. Okay, so in this cycle, if we want to compare with the basic refrigeration cycle or the single stage vapor compression cycle, then we will see that there is no change in the point 1 and 6, okay, and also 5. So that for the base, that 5 is the condenser outlet condition, 1 is the compressor inlet condition, though there is no change in between the 5 and 1. So that's why the cooling capacity will remain same. But if you compare the the work needed for the compressor in this case and the previous case, then you will see that the H1 to that compressor work that will be reduced by using the intercooler. Okay, so basically if you extend the process 1 to 2, isentropic 1 to 2s or 1 to 2, then up to the pressure of the condenser, then if you use the single stage compressor, so that work is basically higher, significantly higher as compared to the that work is significantly higher compared to the work needed by using these two compressors. Okay, another thing is that if you compare with the single stage compression, then we can see that the final discharge temperature, that means the temperature before the condenser. Okay, so that temperature will be significantly reduced by using the multi-stage compression with the intercooler. So basically we can also explain by this way that in a pH diagram, pressure and the PV diagram, pressure and volume diagram, so the 1 to 2 dash, this is basically the compression process for a single stage cycle. Okay, now we are using the multi-stage compression. So for the multi-stage compression, the 1 to 2, this is the your compression process in the first compression, then 2 to 3 the cooling process, then 3 to 4 is again the compression process in the second compressor. Now you can see that this is the enclosed area 2, 2 dash, 4 and 3. If we compare the basic cycle single stage compression and multi-stage compression, then we will see that this area is basically represent the saving of compressor work by using the two-stage compression with the intercooling. Okay, so same explanation we can also get for the pressure and enthalpy diagram. So in a pressure and enthalpy diagram, so basically we can extend the process 1 to 2 up to 2 dash. So basically the 1 to 2 dash, this is the compression process in a single stage compression system or for the basic system. Okay, so the H2 dash minus H1, this is the enthalpy change for the single stage compression system. Okay, so now we are getting the enthalpy change in a compressor H2 minus H1 and for the second compressor H4 minus H3. Okay, so the H1 minus H2 minus H1, that means the compressor, this enthalpy is basically same for both cases. But if you compare the enthalpy difference in between 3 to 4 and 2 to 2 dash, then you will see that the H2 dash minus H2, that is significantly higher as compared to the H4 minus H3. Why we are getting this conclusion? Because what we have already discussed, that the isentropic process or the slope of isentropic process in a pH diagram, that is basically depending on the density of the fluid or the specific volume of the fluid. So we have already seen that the higher density will give the higher slope of the isentropic line in a pH diagram, and lower density means the lower slope of the isentropic line in a pH diagram. So for the same pressure difference, that means the in between the 3 4 and 2 dash. So for both cases the pressure difference are same. Okay, so for the same pressure difference, if we compare the density at point 2 and 3, then we can see that the density at point 3 that is higher as compared to the density at point 2. So that's why the slope of the isentropic line in case of 3 to 4 that will be higher as compared to the process 2 to 2 dash. 2 to 2 dash. So that's why due to that higher slope we will get the lower enthalpy change for the higher slope. Okay, so that means the enthalpy change during the process 3 to 4 that will be significantly lowered as compared to the enthalpy change during the process 2 to 2 dash. Okay, so that means the H2 dash minus H2 that is higher as compared to the H4 minus H3. Okay, so that's why the total enthalpy change during the compression process H2 minus H1 plus H4 minus H3 that is lower as compared to the enthalpy change for the process 1 to 2 dash. That means the H2 dash minus H1. So H2 dash minus H1 that is be higher as compared to the H2 minus H1 plus H4 minus H3. So by using the multi-stage compression with intercooling, we will get the lower compressor inlet work, lower compressor work needed for the system. And another advantage you can see from this figure easily, so even we have seen in the TS diagram also that the discharge temperature, so that will be also reduced. So for the single stage compression discharge temperature is T2 dash and the multi-stage compression discharge temperature is T4. So T2 dash is significantly higher as compared to T4. So the temperature, compressor discharge temperature will be also reduced by using the two-stage compression with intercooling. So our final conclusion is that the cooling capacity will remain same, which I have discussed, because there is no change in the evaporator inlet condition, outlet condition by using the two-stage compression with the intercooling, but the compressor work that will be reduced, which we have already discussed. So by using the two-stage compression with intercooling, the compressor work will reduce, and due to the reduction of compressor work by using the intercooling or two-stage compression with intercooling, the COP of the system that will be also improved, because the COP is equal to cooling capacity by the compressor work. So COP of the system that will improve, and also what I have told that the compressor discharge temperature that will also reduce, and the improvement of the compressor efficiency. So basically the compressor efficiency or compressor isentropic efficiency that is depending on that pressure ratio of the compressor. So the higher pressure ratio of the compressor will give the higher lower value of the isentropic efficiency, and lower compressor work will give the lower value of the compressor efficiency. So for this case, when we are using the two-stage compression, so for each compressor the pressure ratio that will reduce, and due to the reduction of pressure ratio, the compressor isentropic efficiency that will be also higher, that will improve. Okay, so due to the improvement of the compression efficiency, our compressor work will also reduce. So the compressor work will reduce by using the multi-stage compression due to basically two reasons. Okay, so one is due to the enthalpy effect, or due to the slope of the isentropic process in a pH diagram, which I have discussed, and another issue is that with due to the improvement of the compressor isentropic efficiency. Okay, so for these two reasons, ultimately the compressor work that will reduce, and that will ultimately give the improvement of the efficiency in a for a two-stage compression cycle. Okay, so now another question related to this cycle is that we have assumed some intermediate pressure or the pressure in a intercooler pressure. So now question is that if we change the intercooler pressure, then how the system performance will vary. Okay, so that variation we can see in this figure. So first of all, we will see that how the cooling capacity will vary if you vary the intermediate pressure. Okay, so in this graph, basically obviously if for this calculation I have taken the fixed evaporator temperature and fixed condenser temperature for all the refrigerant. Three refrigerant are considered or compared in this graph. Okay, so the evaporator temperature and the condenser temperature are same. Okay, but corresponding saturation temperature, that means the evaporator saturation pressure, evaporator pressure and condenser pressure, those are not same. So that's why the graph has the different pressure range. Okay, so the variation is different pressure range. So how the intermediate pressure, if we change the intermediate pressure, then how the cooling capacity will change, so that we can see in this diagram. So as the different pressure range for the different refrigerant for the same evaporator temperature and condenser temperature, so that we can see in this figure. But if you see the COP, how the COP is varying with respect to the intermediate pressure, so you can see that we will get some optimum pressure, okay, for individual refrigerant, which may give the maximum COP of the system. Okay, so basically what is happening when we will change the intermediate pressure, so for the lower intermediate pressure we will get the very high efficiency in that lower side compressor, that will give the better performance, and for the high pressure, the higher side compressor, that will give the better performance. So that means that if you change the intermediate pressure, then basically the both cases the evaporator temperature will fix. Okay, only the interplay in between the compressor work for the low temperature compressor and high temperature compressor. Okay, so that obviously if you increase the intermediate pressure, then the lower side compressor work, that will increase. Okay, but the higher side compressor work, that will decrease, and you will see that the combination of this work for the low side compressor and high side compressor, that variation is not monotonous. Okay, so that means for at some intermediate pressure we may have get the minimum work required for the compressor. Okay, so that's why we are getting the maximum COP at that intermediate pressure. Okay, so that means this analysis basically and this happen for all the refrigerant. Okay, so that means this analysis leads that, or that says that, okay, so we for every refrigerant there is some intermediate pressure which will give the maximum COP in case of two-stage compression with intercooling. Thank you everybody.